really my pleasure today to introduce Professor Rick Snyder, who has had a very distinguished career. Did his PhD at University of
Iowa State University.
I'm sorry, Ames. Is that as bad as the Eugene Corvallis?
Kind of, yes. Yeah, I think so, yeah.
I'm sorry,
Yeah.
I hope I didn't offend you.
No, that's okay.
And I won't say the year because I don't know. And
Okay.
we don't want to go back that far.
Okay.
Many research articles through 3 decades. You know, when I think of Rick Snyder's work, he's in an enviable position as far as I'm concerned, because there are very few of us that can say that their research has touched the lives of many, many people and had a really dramatic impact on society and the region in which he lives. And Rick really has achieved that. He is one of the founding, or the visionaries that created some irrigation scheduling networks that have cropped up around the world, particularly one of the first, the California Irrigation Management Service, or CIMMS. And that continues to be studied today in terms of how many billions of dollars that he has saved in agriculture in California and in the United States, and how many billions of gallons of water he has saved that have gone to other uses that are more appropriate. And to that, I feel that is something we should strive to have that kind of impact with our research. And I'm sure he has really interesting insights on how that process has evolved and where we're going to go after the fact. So let's welcome Rick.
Okay, thank you very much. As you said, my name is Rick Snyder. I did go to Iowa State University. I got my PhD there in 1980, so I've been at Davis for 33 years now. I'm going to talk to you today about my 3 decades of ET and scheduling research with no end in sight. And I'll start out talking to you a little bit about Bill Pruitt. Bill Pruitt, of course, was the fellow who wrote the FAO 24 publication on evapotranspiration, and I worked with him for probably about 15 years before he retired. And it was interesting because I saw him the last day that he was working. He was there at midnight, the last day that he worked, still cleaning out his office, which he didn't finish, by the way. And it was interesting because he looked at me, he said, you know, I did everything I could to try to solve this problem of ET. He said, there's still a lot to be done. And I'm getting close now, too, to retiring, and I'm going to say the same thing because there's still a lot to be done. Unfortunately, but we are getting closer all the time. So I'm going to, I was trying to figure out what to talk to you about today, and I could narrow down and go into one thing in detail, but I thought it would be more interesting to talk about a variety of things, problems that I ran into in California and things we tried to do. Some of the successes, some of the things I hope will soon be successful, and give you kind of an overview of things that I've worked on in California. I work on probably about 60–70% of the time I work on evapotranspiration, and the rest I usually work on frost protection. So I'm not going to say much about frost protection today, but hopefully I'll give you some insight about evapotranspiration. The topics I'm going to cover are CIMMS, the California Irrigation Management Information System. I was the principal investigator on it with Jerry Hatfield and Elias Ferreras, who's used to be the Minister of Science and Education in Spain after he left Davis. Now he's a professor back at the University of Cordoba. So the 3 of us started CIMMS. It was kind of an adventure. I was the only one who was still employed by the University of California when we finally finished the project. So it tells you how hard it was. And I was new, so I couldn't leave. But it was a difficult project because nobody had done it before. It was the first time somebody had done a network that was specifically for evapotranspiration. And we took some big risks because, and it wasn't easy. We actually fought over a lot about whether or not we should have a distributed system or a centralized system. And we took the risk that we thought that desktop computers and microcomputers were going to take off, and we were right. So we lucked out in the end that we chose to do it that way and make this into more of just a delivery of evapotranspiration information. And so we've always done it from that approach. So it's a little bit different than been taken here at Oregon State. I'm still not sure which one is the best, but I think that our idea that microcomputers, desktop computers would take off was definitely right. I'm going to talk about the adoption of ET-based scheduling, a little bit about things that we've done, some information about what we learned about people when we were trying to set up the CIMMYS project. For example, I thought we knew everything there was to know about crop coefficients and evapotranspiration when I came to Davis. Or I thought they knew everything, and I found out they didn't know everything. And I found out we're still trying to learn things, and we're changing things all the time. So I'm going to talk a little bit about that. I'll talk about climate and crop coefficients, because one of the things I've learned over the years, doing enough measurements now, is I know that crop coefficients are not universal. Absolutely not. If you go to a different climate, they're going to be different. And I know when I studied agronomy at Iowa State University, we always said, you got the crop coefficient, you were done. But it's definitely not true. And I'll give you an example of that, a good example. I'm going to talk about dew, fog, and light rainfall, which is, I'm sure, dear to your hearts here. It's a big problem in California in irrigated agriculture, especially, well, along the coast, mainly along the coast. Because water, the problem is not the estimation of evapotranspiration, the problem is the water balance. And so when I go talk to farmers in California along the coast about evapotranspiration or irrigation scheduling, they always tell me the same thing. Oh, you tell me to put too much water on. And the problem is because the water balance is wrong, because they don't account for dew and fog. And I'm going to talk about that. And we came up with a method to estimate what that fog contribution, dew contribution is to evapotranspiration. And I'll talk a little bit about how we do that. I'm going to talk some about ET measurements over crops. We came up with a new method to estimate evapotranspiration in Davis. They're currently trying to patent it, so I can't tell you all the details, but I can tell you it works pretty good. And we've been playing around with it for about 15 years now. We're just about ready to start putting it out, making it more available to people. We do use it. We have used it for a long time, but we've been calibrated. But we figured out how to do it without calibrating, so that's a big change. And I'll talk a little bit about that. And the last thing, I'll talk a little bit about climate change impacts on irrigation and evapotranspiration. For those of you not familiar with California, this is a topographical map of California, and there's an evapotranspiration map. Central Valley is where most of the agriculture is. In fact, most of it's in the San Joaquin Valley here. This is the Sacramento Valley. San Francisco's here, LA down here, San Diego's down here. The evapotranspiration is really related to the mountains. There's a coast range, of course. We have the Sierra Nevada range of mountains. The ocean dominates the humidity over California. The dew point's about 10 to 12 degrees Celsius almost over the whole state, because it's so dominated by the Pacific Ocean. But if you get way out here in the southeast, you can get a little bit lower humidity. But generally, it's pretty high, or about the same everywhere. Not high, it's pretty low, actually. So now I'm going to skip back into what's CIMMYS. CIMMYS is an automated weather network. It has a database of ETO and weather information that we're trying to give out to the farmers to encourage them to do evapotranspiration-based scheduling. I will point out it's not always the best method for doing irrigation scheduling. There are some examples where it's better to do soil measurements. Some places, high water tables, it's not going to work. Places where you have dew and fog contributions, if you don't account for that, it's not going to work. But if you have well-drained soils and you're able to get a good estimate of what all the contributions to the water budget are, you can use it pretty well. We use it with crop coefficient, KC values, to estimate evapotranspiration of various crops. In California, there's about 130 stations, CIMMYS stations. These are a couple of examples. This is at the Westside Field Station. This one's at Fresno State University. There's about 130 stations around the state. Covers most of the main agricultural regions and a lot of the cities. The cities like CIMMYS a lot because it's good PR for them trying to conserve water, public relations. So they're always trying to get stations, and the state has to say no all the time because it's hard to find good locations to put the stations. So they've done some new things, like we now have the Weather Service is giving out forecasts of evapotranspiration over the state. But you can also get that in Oregon. All you have to do is ask the Weather Service and they'll do it. Because once they've done it in one Weather Service office, all of them have access to it. And so it's really been useful. The farmers love it. So it's really a beneficial thing, and I'm sure you can get it here too. Maybe they have it, I don't know, because they talk to each other. I don't know how much it spreads. For estimating crop evapotranspiration, I call it actual crop evapotranspiration, there's a couple of steps here. First off, we take ETO, and ETO is the reference evapotranspiration. So it's an estimate. Technically, it's a virtual evapotranspiration. It's not even real anymore. They use a standardized reference evapotranspiration equation, but it estimates approximately the evapotranspiration of a 12 centimeter tall cool season grass. But in reality, they use an equation and they put in fixed numbers for the canopy resistance and fixed numbers for the aerodynamic resistance. But that gives you a measure of the evaporative demand, the ETO. And in California, that comes from CIMUS. In order to get the crop evapotranspiration of a well-watered crop, you have to multiply the ETO by a Kc value to get ETC, and that's what the symbol we use for well-watered crop evapotranspiration. And then if you have any kind of water stress or something that's going to affect evapotranspiration, you also have to multiply by a stress factor to get the actual evapotranspiration. So when I go out and measure evapotranspiration, I usually say it's ETA. I don't say it's ETC because ETC implies it's well watered. Unless I've done some kind of measurements where I'm pretty sure it's not stressed, then I would use ETA. So a lot of my graphs I put ETA on it. It's unfortunate. It causes lots of problems. Like when you do wine grapes in California, it's a real problem because farmers stress the grapes on purpose because they get better quality wine grapes. And so that means that they really don't have ETC. They have ETA. They have actual evapotranspiration. And so that, I'm trying to get them away from doing that because they should be applying a stress factor and not a crop coefficient directly. The main reasons for CIMUS, well, of course, one of the reasons was to improve evapotranspiration estimates. When I came to California, there was like 5 or 6 different groups that were giving out ET information, and they had alfalfa reference, they had grass reference, they had pan evaporation, and nobody knew what anybody was talking about. It was a real nightmare when I first came there, and I remember we met with the USDA, the US Bureau of Reclamation, all the universities, and we all got together and we said, we really have to do something because nobody knows what crop coefficients to use. Everybody's got different numbers. And so we finally all agreed to use the ETO, the reference ET for a cool season grass, because that's what Bill Pruitt used, and that's what probably 98% of the world uses. So we went with the reference ET, ETO. But anyway, one of the reasons for doing it was to try and improve the accuracy of evapotranspiration estimation. Of course, another one was water and energy conservation. That was ultimately our goal. The state of California is actually pretty good about it. They want to have the highest production possible, the best possible use of the water for production that they can do. And there's been some remarkable increases in production in California due to changes in irrigation in the last 30 years. For example, the tomato production per unit area is about double what it was 15 years ago. Almond production has gone up probably 50 or 60%. I mean, it's just amazing how much the production has increased in the last 10, 15 years. And a lot of it has to do with better irrigation. Part of it's better irrigation, part of it's better fertilization. So one of the goals, of course, is increase yields and profits. That's one of the reasons why we can convince farmers to do it. They do like getting more profit per unit area for the inputs. One of the reasons why we did CIMUS, and I still believe this is probably the best way to improve irrigation efficiency is to improve the irrigation system. Evapotranspiration is part of it. It's part of the efficiency, but it's not the whole thing. You also have to have a good distribution uniformity. You have to apply the right amount of water, which involves evapotranspiration. So what you're trying to do is get the highest application efficiency that you can get. And that involves trying to improve the irrigation system. And so one of the reasons why we did CIMUS was we wanted to eliminate one of the problems. We wanted to be able to give the farmers the best possible information on how much water they should be applying. And once we did that, then we figured the next step was to go back and really hit them hard with, okay, if you want to really do this right, you need to know your distribution uniformity and figure out how to apply that water efficiently. And so that was always in the back of our mind, one of the main goals was try to do the whole thing. And the other reason was to try and get the farmers to adopt modern irrigation management. Because they tried a lot of different things. When I remember one of the irrigation specialists told me one time that one time they had 35% of the farmers used aerometers, I can't think of the word. Tensiometers, thank you. Tensiometers for irrigation scheduling. And we were walking down this farm field one time, and he was telling me that, and he said, you know where they all are now? And I said, no. He said, they're all out behind the barn. He said, they all quit. You know, and I know in Oregon they found the same thing. Okay, that people would try things, and then after a while they just discard them after a while. So what we wanted to do is try to get people to adopt modern management and keep using it. So that was kind of our goal. This is some information about CIMMYS. It costs about $850,000 a year to maintain and operate CIMMYS. It costs $3.5 million to set up the system. It's not the most expensive. Oklahoma was more expensive than CIMMYS, but they have tornadoes too. So they have more money. We don't have tornadoes. Well, not dangerous ones anyway. So the operational cost, $850,000 a year. The water savings that they estimate, this was a study done by the economists in Berkeley, about 132 million acre feet annual water savings. And the agricultural profits, they estimated only for irrigation, they estimated was $64.7 million a year. And that was in 1990. Parker et al. Parker was irrigation, he was an economist from Berkeley. And they estimated that this is the profit, the additional profits that the farmers were making by adopting and using CIMMYS at that time in 1990. And which is pretty phenomenal that they estimated that. I'm not sure I understand and agree with everything they did, but it's really nice when you're trying to get more money. Because you can say, look, we make 64, yeah. But it's interesting because the reason why they did this was the state was trying to decide whether or not they should charge for the use of CIMMYS data. And they decided based on this, well, if they're making $64.7 million additional profits by using CIMMYS, just the taxes alone more than pay for the $850,000. So they decided not to charge for it. So I use this a lot when I talk to people around the world about, well, should you put out a weather network or not? Absolutely. I mean, you're going to make money. It's going to save money for you. So I don't see any reason why you wouldn't do it. But anyway, it's interesting that's what came out of it. So I got a question for you. We'll give you the answer later, but think about this. What percentage of California farmers what is the percentage of California farmers who ever used evapotranspiration for irrigation scheduling? We asked that question in 1986. We did a survey, and I'm going to find out from you in a little bit what you think. And then today, what do you think it is today? Because adoption is a big problem. You know, you can provide the people with the information, but you have to get them to use it. You have to show them how to do it, encourage them to use it, and then you go back and see, are they using it? What do you need to do to make them use it? And I know that's been a big problem in Oregon for a long time, too. In fact, I think I have, yeah, there's my slide. Marvin Shearer, who was the irrigation specialist at Oregon State. Actually, this is one of the first papers I read when I came to Davis. Was to read this paper because he'd done about the same thing. In fact, I actually kind of stole the title from his title. But he was talking about he had 25 years of modern irrigation scheduling promotional efforts in Oregon, and he was trying to figure out, you know, they were trying to figure out, well, what was successful, what wasn't. And it ended up that he thought the behavioral patterns and attitudes of the people were more important than whether or not the information was accurate and whether it was available and everything. And I kind of agree with him, but I think we learned a few more things since then. Because we kind of started, this paper was 1982. We started CIMMYS in 1982. So this was 25 years ending in 1982. CIMMYS started from there on. So we did a lot of studies during the CIMMYS project to find out why farmers adopt, why they don't adopt, to see what we could do to try to get them to adopt and use evapotranspiration for scheduling. So one of the things we found is the people who are most likely to use any kind of modern irrigation scheduling were people who had problems. If they had a soil problem, if they had an infiltration problem, if they had a salinity problem, if they had a disease problem, if they had problems getting the water when they wanted it, those type of things. Anybody who had some kind of a problem were the people who were most likely to do it. People who didn't have problems, it wasn't a priority for them and they really didn't put much into it. The second thing we found was to get adoption was to work within the limitations. A lot of times You know, I found water districts in California where they only deliver the water every 10 days. Well, what can you do for scheduling if they only give you water every 10 days? Well, at least you can apply the right amount of water every 10 days. Or you can try and encourage the water district to change their policy and change their methodology. But these are the kind of things that we ran into. And I could tell you a lot of examples of things, problems that we ran into and tried to solve. One of the biggest problems I find with people adopting irrigation scheduling is they don't measure their applied water. It's changing now because a lot of people have changed over to drip irrigation, micro sprinklers, and sprinklers from what they used to be. So going from surface irrigation to pressurized systems has improved this a lot. But if you don't know the applied water and you don't know the distribution uniformity, you can't do irrigation scheduling. When we did our survey, we sent out questionnaires to farmers all over the state, and we got a good return. And Ben Faber, who was working with me at the time, he went out. The people who said they used evapotranspiration scheduling, he went and talked to every one of them who said they used it. He went and talked to all of them. So you're talking about quite a bit of time that he put into that. And one of the questions that he asked, because a lot of people said that they did irrigation scheduling with evapotranspiration, and we didn't know whether they really knew what they were talking about or not, because you can't tell when they just fill out a questionnaire. So he went out there and asked them some questions to find out if they knew about irrigation. And if they didn't know the application rate for the irrigation system, they didn't know the distribution uniformity for the irrigation system, we figured they didn't know. Because you can't do it. You have to know those things in order to do scheduling. So that's one of the things that we have to do. We have to teach them how to do those measurements and show them why it's important, or you have to provide a service to do it. And there are services in California. There are private services that will go out and do irrigation evaluations for you. They'll do scheduling, the whole works. Actually, they really tried hard to stop us from doing CIMAS because they wanted to sell weather stations. And so they really resisted a lot, and they said it was going to destroy their business. It didn't. There's probably 3 times as many now as there were when we started CIMAS. So we really helped their business, and which is what we contended from the beginning. It really did help them. They don't sell weather stations, but they got a lot more business because now the farmers are a lot more aware of how important it is, and they can see the benefits. One of the keys is you have to have good record keeping, so irrigation record keeping. The people who are very good at irrigation in California, they can tell you their irrigation records for years. And they look at them, they look at their production, they know what they did different, and they gradually over time they improve. And you need to have agencies to encourage the farmers to do a good job. What we found in our studies was that orchard and vine crops were more likely to do irrigation scheduling than field crops. We found 0 growers who did field crops who did irrigation scheduling in 1986. We couldn't find any. There was none of them. We did find people who had orchard and vine crops who did it. If you had a pressurized system, you were much more likely to do irrigation scheduling than if you didn't. I don't think we found, no, we didn't. We didn't find one person with furrow irrigation who did irrigation scheduling with ET. We found 0. It's not true now, but it was true at that time. We found the education is really important. The places where we had the most people who did irrigation scheduling with ET, they had higher education. The numbers are pretty good. I mean, there's a lot of farmers in California with masters and PhDs. There's quite a few. A lot of retired military pilots and things. There's a lot of people with a lot of education there that are farmers now. And you can't know everything. To know fertility, to know economics, to run your labor, to do irrigation, pest management, it's not an easy job. And sometimes you have to show them that irrigation is important to get them to work on it. One of the things we found is that farmers talk to farmers. So if you find the right farmers that the other farmers respect and you get them to change, the other ones usually follow them. And also when they talk to each other, let me go to this last one. The local water cost, and it's related because we didn't find any relationship between water cost and whether or not farmers used evapotranspiration for scheduling unless they were in the same area. So if they were in the same relative area, then they did because they talked to each other. So I'll give you an example. If you go to Kern County in California, near Bakersfield, if you go to the west side of Kern County, the water costs twice as much as it does on the east side of Kern County. And they get together in meetings all the time. And so if the farmer on the west side finds out that the guy on the east side is only paying half as much for his water, then he thinks, I got to do something to compete, because I have to compete with this guy to make profits. But if you're trying to compare people water costs in LA and San Diego, which is $700 an acre foot, with farmers up near Modesto who pay $1 or $2 an acre foot, there's no compare. You know, they don't look at that. They don't even consider the other one. But locally, it did make a difference. Okay, so back to our question again. It ends up in 1986, we found that 1.5% of the farmers that we surveyed had used evapotranspiration at some time to estimate do their irrigation scheduling. 1.5% is pretty darn low. And that was anything. That was using the evaporation pan, that was using, you know, historical records, or using, you know, some kind of an ET estimate. We did find a few, but we didn't find many. 2010, I would guess that there's between 35 and 40% of them use evapotranspiration to some level. We didn't do a survey on it, but we can tell kind of from the people who use CIMIS and talking to people, we have a pretty good idea. It's somewhere around 35 to 40% of them. But it's also the bigger farmers, so I think it's more than half of the area, irrigated area is done. So the big farms, almost all of them do scheduling. When you get to the moderately big ones, they'll hire consultants to help them, but they usually do scheduling. It's the smaller farmers that we have the most trouble with getting them to adopt. When we did our survey in 1986, we sent out 10,000 questionnaires to 80,000 farmers in California. We got 2,000 responses, which the social scientists told us it was pretty good. 60 out of that 2,000 said yes, they used evapotranspiration. Ben Faber, my colleague, he's now a farm advisor in Ventura. He went out and talked to those 60 farmers to find out whether or not we should believe them or not. And he concluded that only 30 of them probably knew what they were talking about. So it was interesting that because they didn't know their application rates. They didn't know their distribution uniformity. They didn't know their efficiency. So if you don't know that, you can't do scheduling. So they really didn't know what they were saying. But it was an interesting exercise. So I would like to take credit for that we got all those farmers to change and got, you know, 4 million irrigated acres now under scheduling with evapotranspiration, but it really wasn't probably us. I mean, I think the university had an influence. We had a big influence because we taught them about CIMIS, we gave them information, and we helped them with stuff. But I think mainly it's the changes in the irrigation methods. So these are different surveys that were done. There was one in 72, 1980, I think it was 80, or what was it, 88, something like that. And the last one was 2010. To look at the area irrigated by irrigation method. So these are percentages. When I came to California, 80% of the irrigation was with gravity. So it was furrows and level basin and graded basins and so on. That's dropped down to almost 40% now. So it's a huge drop in the surface irrigation. And remember I said we couldn't find one farmer in California who did irrigation scheduling with surface irrigation when we did our survey, who had ever used evapotranspiration for it. So it's gone down to 40%. The thing that's really skyrocketed is the drip irrigation, but that also includes micro sprinklers. So when people plant vineyards now, when I came to California, they didn't irrigate wine grapes. Now they irrigate. Okay, so over a period of about 10 years, they went from zero irrigation to almost everybody. And all the new plantings, all the new wine grape vineyards, almost all of them now have drip irrigation. So it changed dramatically. And you can see it went from near zero up to about 40%. Well, this also includes micro sprinklers, so this is a lot of orchard crops too. Actually, vineyards have increased, but the orchard crops increased a lot. If you ever drive down Interstate 5 down through California, down through the San Joaquin Valley, it used to be on the west side of the San Joaquin Valley, you would see cotton as far as you could see. In the summer, you'd see cotton fields everywhere. Now if you drive down there, you see oranges and you see almonds and walnuts and all tree and vine crops, which is good and bad. It's good as long as they have a source of water. It's really bad if they lose the source of water, because then they're going to lose billions of dollars. But right now it's okay. As long as they keep getting the water, it'll be okay. If they don't have a major drought, it's fine. There hasn't been hardly any changes in the sprinklers. It hasn't changed very much at all. And the other includes things like they block up drain tiles in the delta and they back the water up into the field. So there are people who do things like that too. Not very many, but there are a few. Changes in cropping. The field crops was up about 67% back in 1972. It's down to about 41% now. And the orchard crops have gone from about 15% up to 30%, so it's doubled. And the wine grapes went from 6% up to about 14%. So it more than doubled. It's still not as much as the orchard crops, but there's been a big increase. It's interesting, the other day I was listening to the radio and they were comparing the profits from wine grapes with another industry in California because they were talking about jobs. And it was interesting. I had no idea about this, but they said that the diamond industry in California makes 5 times as much profit as the wine grape industry. And it's just diamonds coming through, being processed and shipped out again. I had no idea, but they said there's not very many people employed in that industry. But it's interesting how, and that's one reason why a lot of times, I'll talk about drought later and possibility of drought. And the economists always say it's not a big deal with drought because the agriculture is only 5% of the California economy. But it is a big deal, especially if you're a farmer. You know, it's really important. And the social network, all the structure would just be destroyed by a major drought in California. So I think sometimes they don't think through everything. Okay, I'm going to change again. I'm going to talk about crop coefficients as a function of climate, just to give you an idea of how it's different, how it varies depending on where you are. I'm only going to give you one example, and it's about alfalfa example, because it's easy. It's easy to show you this, to do the calculations. But we're looking at rice, trying to look at differences in evapotranspiration, whether there's a climate effect, and we're also looking at almonds. And it's not finished yet, but we are still working on it. I used the Penman-Monteith equation, which is right there. The thing that determines evapotranspiration rates, the differences between the reference ET and the various crops, there's really 3 things that vary. One of them is net radiation, because there are differences in net radiation. For example, an almond orchard has a net radiation about 20% higher than ET of grass, than grass does, which is the reference surface. The aerodynamic resistance, so it's the resistance due to the transfer of heat from the air, to or from the air, and that really depends on the difference between the canopy temperature and the air temperature, how rough the surface is, and how much the wind is blowing. So there's 3 things that affect that. And then the canopy resistance, which is a physiological difference between the plants. So if you vary these 3 different things, if you change the climate and look at the difference in the evapotranspiration of one crop versus the reference crop, it gives you an idea whether or not these crop coefficients should change. So what I did was I made a spreadsheet. I'm not going to show you the spreadsheet, but I made a spreadsheet that calculated the Penman-Monteith equation, and I was able to put in different values for the canopy resistance and the aerodynamic resistance. And I used alfalfa because there's already a standardized equation for alfalfa too. And so these are the values that go in for, this is for grass reference, and this is for, that's for grass reference, ETR. And so you can put in these values and you can calculate the crop coefficient difference. So I did that, and I used 4 different locations just to give you an idea. So one is Tule Lake, which is up in northeastern California. I picked places that had very different climate. Twitchell Island is an island in the Delta, Sacramento-San Joaquin River Delta. Torrey Pines is kind of a ritzy golf course down near San Diego. It's right next to the UC San Diego. And Meadowland is a desert research station down in the Imperial Valley near the Mexican border. And just to give you an idea, this is a plot of the ETR, which is the alfalfa, versus the ETO, and this is Twitchell Island. And so this will give you an idea of what the crop coefficient might be, but it's about 1.4, about 42% higher for the alfalfa on Twitchell Island. If I go to Meadowland, which is the one in the desert near Mexico, it's 1.37. If I go to Tule Lake, which is northeastern California near the Oregon border, it's about 1.28. If I go to Torrey Pines, which is that golf course right near San Diego, it's down to 1.16. So there's a huge difference in the crop coefficient for the same crop. So clearly you can't take one crop coefficient and use it. I remember when I was in Iowa, I thought if I got the crop coefficient for corn, it's going to work everywhere, and it doesn't. And the other problem you have now is with the standardized equation, you have fixed values you put in for canopy resistance and aerodynamic resistance. And you know, in California in the winter, I ran into this when I was doing measurements on citrus in the winter because the plants get wet. And when they get wet, the canopy resistance goes to 0. Well, the reference ET doesn't change. It still stays at the fixed value. So if I'm doing daytime standardized reference ET, the fixed canopy resistance is 50 seconds per meter. But if the orange trees are wet, then it's 0. If they're dry, it's probably more than 50 seconds per meter. And I don't know whether they're wet or dry or not. So, you know, one thing I can tell you for sure is you're never going to get it exactly right. You're never going to get a crop coefficient that's universally going to work everywhere. It's not going to happen. Okay, so what we're trying to do is get close. It's like I tell my class all the time. All we're trying to do is minimize the error and get as close as we can, because you never get it perfect, because you don't know everything. You don't have all the information. But this illustrates, again, that crop coefficients do vary depending on the climate. It's very clear there. Okay, I want to talk a little bit about fog. I mentioned back at the beginning that fog is a big problem in California. And when I go to like Salinas Valley, they grow a lot of vegetables and stuff in Salinas Valley. Hell, I go down to Southern California to the Oxnard Plain near Los Angeles, and they get a lot of fog there. And every time I talk to the farmers, I hate to go talk to them actually, because every time I do it, they tell me I'm wrong. And you know, they're not shy. They'll say, no, that's too much. I'll say, this is the evapotranspiration. This is, you know, for your crop in, say, in the Oxnard Plain, which is near Ventura, California, near Los Angeles. And I'll say, this is the evapotranspiration for the last week. And they say, I don't put that much water on. They say it all the time. And they say, so your ET must be wrong. I say, no, the ET is right. The ET is not the problem. The problem is that they get fog all the time. And one of the reasons why I noticed this too is one of the CIMA stations we had was near Santa Maria, California. So it's kind of out near Santa Barbara. It's very close to where Michael Jackson lived. But we had a CIMA station there, and there's a rain gauge on it. And there wouldn't be any rain at all, and we get 2 millimeters of rainfall every day, and there was no rain. And I kept talking to the farm advisor about it, and he said, well, come down and look at it yourself. So I went out there with him in the morning, and it was sopping wet from fog that had been intercepted by the rain gauge and was dripping into the rain gauge, and it takes 1 millimeter and it tips. And it was getting 2 millimeters of tips, you know, 2 millimeters of rain every day. And, you know, the way to get around, you could, you know, the problem there was fog. You can also get that with dew. You can get it with light rainfall. If people don't record this stuff, if you don't have any way to measure or record it, there's no way to do the water balance. So if you have a place, if you're not going to do that, if you want to use evapotranspiration, you have to somehow adjust for the fog and the dew. You have to make some kind of an adjustment for it. Otherwise, you could use soil-based measurement. You could do it with a soil-based measurement, and that would resolve the problem too. Okay, but you have to do it accurately, and you have to do enough measurements to get an accurate estimate. Well, anyway, so I had to come up with an estimate of this because California wants to know, well, how much water do we need for irrigation on the coast? Well, then we have to account for this fog. Just to give you an idea, years ago there was a guy named Acevedo. It's not the one that you guys know. It's a different Acevedo, but he did measurements on forest, on fog drip out of forests in California. He got 30 inches a year of water dripping off the trees, not from rainfall, just dripping off the trees from fog interception. So 30 inches is, what is that? I don't even know what it is in metric. It's quite a bit. 30 inches is like that. So anyway, so it was amazing. That was I think it was in Mira Woods, which is a redwood forest near San Francisco. So it's amazing how much they get. I took 30 stations in California and a wide range of climates. You know, down in the south, you know, in the desert down here, they might get, I don't know, maybe 100 millimeters of rain a year, or something like that. And up here on the north coast, they'll get 2,500 millimeters a year. So there's a huge difference in rainfall from the north to the south. Some of these are up in the mountains, some of them are in the Central Valley, some of them are on the coast. And what I wanted to do is come up with a way that I could try and adjust for this fog contribution. I don't have any instrumentation that can tell me exactly whether the plants are wet or not. You know, I mean, there is instrumentation, but I haven't found one that's universally applicable yet. But I'd like to be able to find something we can do it. So it's based on observation. What I did was, again, I took the Pym-Monteith equation. This is the daytime equation that you'd use during daylight hours, and this is for nighttime, and I used those equations. I took data from all those 30 stations, and I calculated, this is only for Davis, just to give you an idea. But I took 4 months, March, June, September, and December, for each of these 30 stations. I calculated the daily or the hourly ETO rates. And then what I did was, so I did that for each hour, and I did it for each of those 4 months. And then I did this for the 30 stations. And I took that, and it ends up that this is the curve that I came up with using all those, and these are the standard deviation bars. I was really kind of surprised too. I didn't realize that it would come out that well. You know, there's some variability here. If you look at the other sites, I'm only showing you Davis, but there were 30 sites total, but they all look pretty much like this. Some of them have a little bit more spread than others, but most of them are pretty close to this. And so when I took all 30 of them, I did the standard deviation. You can see the bars there, that it came out pretty good. Found this equation that fit it pretty well. This x0 is the value where half of it's above and half of it's below. It ends up, it was 12.5. And I used Solver in Excel to solve for these two values, and this is what it came up with. And so what this tells me is that if I know that the fog dries off about, say, 10 o'clock, if I come up here to this point, I come over there, it looks like about 20%. So about 20% of the evapotranspiration probably came from the fog. 80% probably came out of the soil. If I waited until noon, if it dried off about noon, and I've seen that a lot if you go to Watsonville and Santa Cruz and Monterey, places like that, the fog interception will dry off around noon. If I come up to there, I come back over here, it's about, I can't tell from here, 45%. So that would say that 45% of the evapotranspiration came from the fog. So that means 55% probably came out of the soil. So it's just a rough way of estimating what the fog contribution is to evapotranspiration, which then we can adjust and estimate how much came out of the soil. Alternatively, you'd have to measure the soil moisture, which is, my way of thinking, is more difficult. Okay? So this is the method we came up with. And this is, we've integrated this into models that we use in California to estimate water resources, how much we need in different areas. So we're doing that. The problem is you have to know when it dries off. It works pretty well in the urban areas in Southern California, because you go to Los Angeles and San Diego, in the morning you go out there and the grass is all wet. You know, it might be 10 o'clock, 11 o'clock before it dries off. And so if they're using evapotranspiration directly, they're over applying the water. They're putting too much on, because some of it's coming, because that water has to evaporate off the plants before it starts to take water out of the field. It's an energy balance problem. Okay? So anyway, that was one of our things that we figured out that is helping, so now we can cover the whole state. So now I talk a little bit about measurements. I've been making a lot of measurements in rice. Almonds, walnuts, citrus. I can't talk about all of them. I'll just kind of give you a little bit of an overview. But we've done a lot of measurements in rice the last few years. What we do is we estimate evapotranspiration using the residual of the energy balance equation. So we calculate the latent heat flux, LE, is equal to the net radiation minus the ground heat flux minus the sensible heat flux. Generally what happens on a daily basis, the G is going to come out close to 0. So it ends up that your LE is probably going to be mostly net radiation minus any kind of sensible heat flux if you average it over the whole day. It ends up that, you know, unless you have really severe conditions, this is pretty small. This is close to 0, so it's mostly net radiation. But you can, if you have windy conditions, or depends on where you're at, that H value can be important. So that's sensible heat. Heat that's either coming out of the air to provide extra energy to vaporize the water, or heat that's going away from the surface. So we use that, and then of course we calculate the evapotranspiration by dividing by L, the latent heat of vaporization. We use the sonic anemometer to get our values for H. I actually found cheap ones, and they work pretty good. They're not bad. For the price, they're excellent for the price. This is RM Young sonic anemometer. They're not as good as some of them that you can buy, but these are only $3,200 as opposed to, you know, it could be anywhere up to $20,000 or $30,000 if you get really super good ones. But it seems to work pretty well, and we've tested it against lysimeters, we've tested it against a lot of different things, and they're pretty good. It was recommended to me. Tilden Myers did some research on it, and he compared a whole bunch of different ones, and he said, well, I just get for your purposes, I just get the RM Young. And it seems to work pretty well. The only problem we had is birds. We had an eagle sit on one time and broke it. But that's been the biggest problem. One of the things that we're trying to do is we're trying to figure out a cheaper way, a simpler way to get evapotranspiration. And of course, the sonic anemometer is, this is $2,300. I'm sorry, $3,200. Got it backwards. $3,200 for one of this. And this is the cheapest one you can buy. And we're trying to replace it with this, with a thermocouple, which you can buy for $105. So one of the things we've been working on for a long time is called the surface renewal method. It was developed by my two colleagues in Davis. The first one was Roger Shaw, who is a micrometeorologist, and he came up with the idea of coherent structures in plant canopies, which has to do, when I was a student, I remember my professor used to always say that if you took fine wire thermocouples and you made measurements, you get lots of variability, a lot of fluctuations. He said it's all just random noise. And Roger Shaw did studies on it in a forest up in Canada when he was on sabbatical, and he came back and he showed it to us, and it was very clear that you could see ramps in the data, and you could see, if you made measurements at different heights, you'd see the temperature would drop at the highest one, then the next one, then the next one, then the next one. So you could see it was cold air coming into the canopy. Then it would go out and another bubble of air would come in and replace it. And so it would sit there for a while, it would bounce out and another one would come in. So you could have cold air come in or you could have warm air come in. Happens all the time. It's really interesting to go out with a fine wire thermocouple and just sit there and watch it and put it on your data logger and watch it. And you can watch when it graphs and you can see this thing going up and down. It's really amazing. It happens all the time, 24 hours a day. Whether it's stable or unstable, it still happens. So what we're trying to do is figure out how we can use these to estimate the sensible heat flux. Well, Roger Shaw came up with coherent structures. He's the one that figured out, okay, it's because of these bubbles of air coming in and out. My other colleague, Chelta Pau, said, well, if that's true, then if we can, if we look at these ramps that you could see in the data, he said, well, then I get the change in temperature with time. And if you can get an average change in temperature with time over, say, a half-hour period or something, and you multiply that by the volumetric heat capacity and the volume, you've got sensible heat flux. And so that's the basis. So the big problem was, how do you get an average ramp out of this data with all these fluctuations in it? Well, he went back to the literature and found a paper by Van Atta, who was a mechanical engineer down at Caltech back in the 70s, and that paper explained how to do it. And so we've been doing it ever since. And so it worked out really well. The only problem that we've had is these are 3,000th inch diameter fine wire thermocouples, and they're too big. If we could get them smaller, it would be more accurate. And we knew that from the beginning, but the problem is if you put smaller ones out there, they break. 3,000th inch diameter, if I put this out, sometimes they'll go for 2 or 3 months and they won't be broken. But if I put out the fine ones, they're lucky if they would last a week. So we've tried 1,000th inch diameter, and we tried 10,000th inch diameter, and they'll last a day or two, and they'll be broken. So one of our students who just recently got his PhD figured out how to estimate the really super fine ones by our temperatures from these. And so he's figured out how to do the surface renewal without calibration, because we've been calibrating for a long time against a sonic anemometer. So he's figured it out. That's what he's trying to patent right now. And once we get that done, then it'll start being available to the public. This is what I was talking about with the ramps. If you look right here, this is a good example. If you see this temperature, this is over wheat. The wheat was about 0.7 meters tall. This was measured right at the top of the canopy. This was measured at 1 meter, and that's at 1.3 meters. This is 60 seconds of data. The temperature was measured at 8 hertz, 8 times a second. And you can see here that the temperature dropped, and then just slightly later you can see the temperature dropped here, and here you can see the temperature dropped there. So you can tell that there was cold air coming in from above down into the canopy. It sits there for a while and it gradually warms up. You can see it this is not the best ramps, but they're okay. Here's a better one. You can see it's gradually warming up. And it might do this for a while and then it'll drop again later. I don't have one there, but it gradually warms up and it drops again. Well, when we do this analysis, this statistical analysis, we get an average ramp. So we get the change in temperature with time, and then we just put it into an energy balance equation, and we've got the sensible heat flux. And we've compared it with sonic anemometer. It's pretty darn good. Comes out pretty well most of the time. It has some advantages because the fetch requirement is much less. Fetch requirement for this is probably 10 to 1. You know, and I wouldn't go under 50 to 1 minimum for a sonic anemometer. Okay, so it allows you to do edge experiments, and it also allows you to do urban, which is a big problem because, you know, in urban environments, the ET is much more difficult than in agriculture. You don't have these big fields, you have small fields. So it offers a chance for us to try and improve urban estimates of ET as well. This is just a calibration curve I just put in to show you. This is a plot of the uncalibrated, this H prime is the uncalibrated surface renewal measurements, and this is the sonic anemometer. And you can see the regression is pretty darn good, R squared of 0.86. The slope is 0.65. The 0.65 is our calibration factor. So it means if I measured H prime with my thermocouple, I can multiply by 0.65, and I have a pretty good estimate of what the sonic H is. So we've been doing that for 15 years, but Tom, our student, Tom Chaplin, figured out how to do this correction for the size of the thermocouples, and we found out that the calibration factor is the same for all crops. That's what he found out, if you make this correction for the thermocouple size. So that's what they're trying to patent. This is just to give you an idea of some of the things we learned. This is an example. This was one of the early experiments. These are my two Italian colleagues. She's from Sardinia and he's from Sicily. And I told them they couldn't speak Italian to each other. But they were out there. We're setting up a station. This is one of the early ones we did. You can see there's a station out in the middle of a rice field. This is before we put it in. This is our little device. You see the toilet bowl, that thing? It makes it go up and down because you have to measure the heat storage in the water. And it goes up and down all the time because they're always increasing and decreasing the water level. So anyway, we did that. We did surface renewal. We did the, I don't know where the sonic is there. It's out there somewhere. But we did the sonic anemometer, we did the surface renewal, and we always compare them. So if the sonic goes out for some reason, we still have the surface renewal or vice versa. And we always check them against each other, and they usually come out pretty close to the same. The reason why we were doing the rice work is, this is the reason why we did it. This was a paper by Lawrence and Pruitt. Fred Lawrence was a farmer in Red Bluff, California, but he's also probably made more lysimeters than anybody in the world. He's I guess he was mechanical engineering, but anyway, he worked with Bill Pruitt when he was at Davis, and they did measurements in rice fields. You know, and Pruitt wrote up FAO24, which is kind of the Bible of crop coefficients, and I always wondered why the crop coefficients were so high for rice, because this was his paper. And what this is the mean. The red ones were what he came out with for his estimates of what the crop coefficient should be. So for June, the mean, he said, was about looks like 1.02 or so, 1.03 or 4. You know, but they're pretty small, pretty close to 1, not that much higher than 1. So this is what he published in the paper with Lawrence, and this is what the state of California uses, 1.17, 1.26, 1.17, so way higher. And you know, the state guys didn't even know about this. It was interesting. I was talking to them, and they didn't even know about this difference. But this is what they have published and what they use for estimating the evapotranspiration rice. So it's part of the reason why they think rice uses so much water. It doesn't. It's not that much different than other crops. It's not that much different at all. The reason why this happened was because they were measuring the evapotranspiration of a rice field about 30 miles north of Davis, 30 or 40 miles north of Davis, and they were measuring the reference ET in the lysimeter with grass in the lysimeter in Davis. And they had evaporation pan up by the rice field, and they had one back by the lysimeter. It ended up that the evaporation from the pan in Davis was about 15% higher than the evaporation from the pan up by the rice field. So they assumed that if the lysimeter had been up by the rice field, that the reference ET would have been lower, so they raised the crop coefficient. And so that got put in FAO24, and so everybody in the world's been using the wrong numbers for the last 30 or 40 years. And you know, this is what they actually published. And when I did my experiments, I get about the same thing all the time. So the evaporation pan was their downfall. in that case. This is an example of a KC curve. The green one is a KC curve for rice. And the first time I saw this, I thought, oh, I did something wrong. Because when you usually see crop coefficients curves, they start low, they go up, they level off, and they fall down. This one didn't. It started high, went down, leveled off, and then went down. The reason why this happens in rice fields is because the net radiation. The net radiation over water, when you first plant the rice, they flood the field, they fly over with an airplane and drop the seeds into the water. And so it's just open water. It's just a water paddy for a while. It takes a while for the rice to start growing. And so this early part, this is the net radiation. This is net radiation for grass. This is the net radiation we measured over the rice field. And this was rain. It's unusual that we get rain then, but we did. And you can see the net radiation decreases until it's almost the same as the grass later on in the season. Once the canopy grows up fully, then there's not much difference between them. But early on, when you just have water, the net radiation is higher. So that's why the evapotranspiration, the KC value is high early and it drops off. This is an orange orchard. This is Josephine is from Beirut, Lebanon, and Simona is a professor from Catania in Sicily, and they were working with me on this project. This was actually a 4-year project. This was the last year of the 4-year project. These orange trees are about as big as you're going to see anywhere. These are huge orange trees. This was at sunrise, and east was behind me. I took this picture looking to the west. And they plant the rows east and west because they worry about frost is one of their biggest problems. They want the cold air to drain through the orchard and go out the other side. If they put them the other way, it would hit the trees and it wouldn't go through. So they do it this way. But I showed this to one of the guys from the Department of Water Resources. He used to live down there and work down there. And he's been up in Northern California where they don't have much citrus for about the last 10 years, 10, 15 years. And when I showed this picture, he said, "What is that?" He didn't recognize the trees. Because in 15 years, they've changed dramatically. I mean, these are 4.3 meters high. There's not much, it's pretty hard to get through there. You're seeing sunlight on the ground right now, but a half hour later, all the sunlight's intercepted by the trees, and it stays intercepted all day. There's no light reaching the ground. If you go under there, you can see how dark it is under there. Once a half hour later, when it's intercepting all the light, the rest of the day, it's dark under there. It's intercepting every bit of sunlight that's there. There's a big controversy over what's the crop coefficient for citrus trees. If you look in FAL 56, it says it should be 0.67. But that's based on measurements that were done in Valencia in Spain. And the trees were about 1/3 the size of these. And they consider that mature trees in Spain, but they're not mature trees in California. And so the ET of these is much higher. And this is showing you the 4 years. This was the first year. The first year they pruned it. They pruned it back a lot. They topped it, so they cut off about the top meter or so of the tree. They pruned them back severely. And you can see it started out about 0.6 something, and then it went up during the season. At the end of the season, it's up to what? It's like about 0.7, 0.75, something like that. This is the next year. You can see it went up all the way up to 1 by the end of the season. This is the 2003 was the 3rd season, and this was the last season. So it looks to me like the KC for the mature crop, when it's intercepting all the sunlight, is about 1 during the mid-season. The winter, it's jumping up and down because of the fog I was telling you about. Central Valley is full of fog in the summer, or in the winter, not the summer. Summer is no fog. In the winter, there's a lot of fog. The trees get wet. Also, the instruments get wet. So the measurements, when you make measurements in the winter, it's always a problem. Because you get wet sensors, they're not right. You can't use them. I just left them in there, but generally, you can see the crop coefficient's about 1. I put this in. This is from Sicily. This is Alfonso. He's the guy who was in the rice field earlier. This is from Sicily, where this is an orange orchard in Sicily, just to show you the difference. Look at the difference between these trees and the ones that are in California. Look at all the light getting through to the ground. Look at how they pruned it up all around the trees and stuff. It's completely different. The crop coefficient they got making measurements in this orchard was about 0.85. The ones that we got were around 1. Okay, but it's pretty clear to see the difference. The sunlight's reaching the ground here, so this is not intercepting all the light. So I'm pretty well convinced that our crop coefficients of 1 are probably right. Okay, and if you look at the trees that were done in Valencia where they used for the FAO 56 publication, they're even smaller than these. So that's part of the problem is you have to, I always tell people, you have to find out what they did the measurements on when they came up with the KC and then check to see whether yours are similar. If they're not similar, then you need to do something different. I wanted to show you this. This is an adoption problem because, okay, this one right here is the applied water and precipitation. And it wasn't the full year, I can't remember, but most of the year. This is the ETC that we measured. This was that first year after they pruned it. This was the yield in that orchard, and this was the county-wide yield. That was 2001. This is 2002. Look at how the yield went up. Remember how the trees were growing up? Look at in 2003. It's more than double the county average yield. We had more than twice as much production of the best fruit than the county average in 2003. 2004 wasn't, it went down because usually when you have a heavy load one year, the next year is lower. But even so, the production was just much, much higher. And you know, the reason is because this grower's putting more water on. They're getting lower yields because they're not putting enough water on. And we can't get the farmers to change. They don't believe us. It's really strange that they don't believe us. Even the farmer we worked with didn't believe us because he said, oh, I use KC of 0.65. But it comes back to the problem I mentioned to you earlier, is if you don't know your application rate, you don't know. And his problem was he took what the company was that sold him the system. It was a micro sprinkler system, and he used their application rate, but he never measured it himself. We measured it. In this case, his application rate was about 30 or 40% higher than he thought it was. And so it ended up that the application matched up pretty well with what the ET was. He thought it was a lot less. So you can't go by what the manufacturer says. I have just a couple of slides. I put this up here. People ask me all the time about climate change and effects on crops in California, because I'm a biometeorologist, so I do anything related to biology and weather. But you know, 18,000 years ago, the ice was about 2 kilometers thick over much of North America. And the temperature was, the mean temperature, Earth temperature was 10 degrees Celsius. Now, the global mean temperature is about 15 degrees Celsius, and the ice is gone. And they're predicting the global mean temperature to be 16 degrees to 21 degrees Celsius, depending on who you look at. But most of the latest ones say up around 19 or 20 degrees Celsius. So it's almost the same higher by the end of this century as it was 18,000 years ago. And so if you'd lost all that ice just due to that change, what's going to happen if you go from this to say 20 degrees Celsius in 100 years? And so I think people really need to be worried. But I don't think they need to be worried about ET. So I'm going to go through this quickly because I know I'm getting late. What I did was I went and looked at the study by Long et al. This is one of the FACE studies. And we took the Stomata Conductance that they measured for grass, which is our reference surface. And this is CO2 concentration. You can see 372 when they did the experiment. They went up to 550 and they did 700. And we got a linear relationship between the Stomata Conductance and the CO2 concentration. I'm going to concentrate on the 550, which is one of the things they're predicting, one of the ones. If I convert that to Stomata Resistance, conductance is one, the reciprocal gives you the resistance. And so for 370 parts per million, it's about 100 seconds per meter. 550, it's about 125. 700 parts per million is about 158. And then if I calculate the canopy resistance, the way you do that, I did the same method that was used to figure out the standardized reference ET equation. And what he did, this is what Rick Ellen did when he came up with it. He took the canopy resistance is equal to the stomatal resistance, which is 100 seconds per meter from that previous slide. And he divided by half of the LAI. And the LAI estimated is 2.88, so that's how he came up with the 70 seconds per meter. That's in the standardized ETO equation. So instead of using the 100 seconds per meter, let me go back, I'm going to use the 125. So if I put in 125, it comes out to 87 seconds per meter. If I use the, what was the other one? 700 parts per million, or 158. If I put in 158, it comes up to 110. Okay, so I use the 87 seconds per meter for the canopy resistance, or for the canopy resistance. I took a bunch of stations in California. I took the current conditions, CO2 372, it's actually close to 400 now. Solar radiation 100, I used the same percentage. Maximum temperature I didn't change, minimum dew point. And I took the data from all these stations and I calculated what it was. Then I did a projection. Well, what happens if I go to 550 parts per million? I don't change the solar radiation. I increase the maximum temperature by 2 degrees, increase the minimum by 4 degrees, and I increase the dew point by 4 degrees. Okay, because one of the things they're predicting is the humidity is going to go up too. And so far, the vapor pressure deficit hasn't changed, which means that the dew point's probably going up about the same as the minimum. And so I used those numbers, I used all those stations, and I went through and calculated. And this is a plot that shows the change from the current ETO, so the current ETO would be 0, versus mean annual wind speed. And it's interesting because if you have really low wind speeds, it means the ETO is probably going to go up. So if you're someplace where there's not very much wind, I expect the ETO to go up a bit. If I'm in a place that has more wind, then I expect the ETO to go down. In most places, you have more wind. This is 1.7 meters per second, which is really low wind. Davis is about 2 to 3 meters per second, kind of average. So basically what it says is that most places I expect the ETO to go down under those conditions. And it's going down because the canopy resistance is increasing because of the CO2, because the humidity is going up. Anything that decreases evapotranspiration, humidity goes up. And the minimum temperature is going up about twice as fast as the maximum. And so those are not unreasonable things to put in for estimates of how things might change. One of the things that I'm worried about, and I've already seen this in California, is not evapotranspiration is the problem. There's two problems that I can see. One of them is drought. I'll show you that in a minute. And the other one is heat stress. Because one thing that is likely to happen, what this is showing is the difference between the canopy temperature and the air temperature. So again, I use the Pimmin-Monteith equation. These circles are the projected canopy temperature and the current canopy. The blue is the current one, the red one is the projected. So it projects that the canopy temperature is going to go up faster, higher than the current canopy temperature, but it's going up more. The air temperature is going up, but the difference between the canopy temperatures is even bigger. Okay, so what that says is that it's likely that plant temperatures are going to get higher go up more than the air temperatures do. So we're always talking about air temperatures, but they forget the plant temperature is the important thing. Now, this is for all the current weather data that I have, and this is, where's this at? Oh, this is Davis, okay? This is all the current conditions in Davis, except that I did I used the 550 parts per million, the other stuff. This is if I reduce the wind speed by 1 meter per second. Look at how much that canopy temperature went up. If I reduce the average by 2 meters per second, look at where it went up to. So if the wind speeds go down, we're in big trouble, because plant cells die at about 50 degrees Celsius. So that's one of the things I'm worried about. And I've already seen it in California. I had a meeting with some farmers one time, and I was with the farm advisor, citrus farm advisor, and we had a breakfast meeting, and we asked him, what are the things that really worry you the most? And I still remember this one farmer, he looks at us, he says, what worries me the most, he said, because they grow citrus on the east side of the San Joaquin Valley. It's on the foothills because the cold air drains off the hill so they don't get frost. He said, the thing that scares me the most is when they have hot, humid air comes into the San Joaquin Valley, so it might be, 40 degrees Celsius, so like 104 Fahrenheit. And he said then the clouds start to form over the Sierra Nevada mountains, and they start to back up. So the humidity is coming in, which is causing the clouds to form. Humidity increases. He said the wind's blowing, he said the clouds back up, and he said then the wind stops, and he said the trees wilt. And they're well watered. I said, well, did you irrigate them? He said, yeah, they're well watered. He said, it scares me to death. He said, the first time I saw it, I thought I was going to die. He said, I was going to have a heart attack when I saw this happen. And I remember the farm advisor was sitting with me, the UC farm advisor, and he says, I've never seen that. And another farmer that was there says, I have. And he said, I have the same fear. And I went and talked to the plant physiologist, the tree physiologist in Davis, and all of them said they didn't know what it was. And the other interesting thing is I talked to Paul Brown, who's my counterpart at the University of Arizona, and he and his wife were doing studies on cotton plants, and they saw the same thing in cotton plants in Arizona. When the humidity comes up from Mexico and the wind stops, he says the plants all wilt, even though they're well watered. And I'm sure this is what it is. I'm sure that's what it is, because you're stopping you still have the radiation coming in, you still have the high temperatures, and you slow down the transpiration because you increase the humidity and you stop the wind speed, and that causes the temperature to go up. And I asked Ken Schockel, our tree physiologist, about it. He said, yeah, that could be it. Might be it. You know, it depends on how long it's there. They're already having trouble with some crops in California. Cherries are having trouble with heat already. So anyway, that's one of the things that I'm worried about. It could get worse. The other thing is drought. And I'll stop. This is my last slide. This is showing the drought in inches, but this is during the period during the emissions in California. Now I want you to look at that drought. That's about 1755 up to about the gold rush. So we're talking about almost 100 years of drought. It was far worse than anything we've seen. This is in the 1800s, 1860 to about 1875. The drought during the Depression was nothing compared to that before. And you know, these are the droughts we've had recently where they just panic and go crazy over they don't have enough water. But what happens if you have something like that again? And that's natural variation. That has nothing to do with, you know, human-induced climate change. So these are the things that I'm worried about. And part of the problem is planting all those trees in the San Joaquin Valley, all the trees and grapevines, because if that happens, they're all going to die because they won't have enough water. They'll save them for a while because they'll pay a lot of money to the rice growers to get their water so they can keep the trees alive, but that'll only be good for 4 or 5 years. And so they have big problems. And you know, the interesting thing is when the state built the canal down the west side of the San Joaquin Valley, they said you couldn't plant permanent crops there. But they all forgot. So everybody forgot, including the banks who gave the money to the farmers to plant there. So sometimes you have to go back and look at what people, I mean, they recognized it before they built the canal. So that was like 70 or 80 years ago, whatever it was. Well, it couldn't have been that long ago. When was it? When was Amerocho did the canal? Do you remember? 80s?
Yeah.
Well, the canal was before the 80s, wasn't it?
The canal was before the 80s,
Yeah.
70s.
Yeah, in the 70s, okay. But anyway, this is what we're worried about, and that's natural change. So when you have man-induced change, who knows? I think that's the last slide. Yep, that's it.
So we're running a little low on time, but just to remind everyone, there is the reception afterwards for in-depth conversation. If anyone has a quick question before we go retire to the hors d'oeuvres.
I must have answered all the questions.
Charles, did you go? I was going to ask in the reception.
Okay.
All right.
Okay.
If there's no pressing stuff, then we'll all talk about reception.